Default view. Let's hope the sound works as it usually does. Default view. Let's hope the sound works as it usually does. Alright. Also, this is like the wrong view, but okay, whatever. Hello everyone, welcome to the Vulkan stream. We had a pretty good stream yesterday where we substantially sped up our mesh shading pipeline, and we've implemented support for push constants, which allowed us to render a bunch of kittens on screen and whatever other meshes you might have using multiple draw calls right now, but this is using the cluster culling, so we can hold on, we can like enable visualization for the clusters, and they're pretty small at this scale, right? And then we can cull them, and it's not visible right now, but we can do the usual thing that we sometimes do where we flip the culling and we see things work. I guess let's do that, because I haven't actually checked in a while that our culling works. So today, in general, right, when I started this project, I had a certain idea about the things that we want to experiment with, right? One of these things was cluster culling, so I think we've done it justice. You can also do cluster culling without using the mesh shading pipeline, but I don't really want to do this because it's kind of painful a bit. It's not as interesting because you have to fill essentially index buffers, and if you have a lot of meshes on screen, that's a lot of memory, you have to budget that. So kind of don't really want to do this. I think we should just, hey, if somebody wants to do this on their own based on this project, like implement cluster culling outside of mesh shading pipeline, great, but I don't want to do this myself. The other things that I wanted to do were essentially the full scope that I had was a renderer that's completely GPU driven, so like culling and submission and all of that happens on the GPU, and we do occlusion culling, and we do like everything that can make the scene run fast, and then we support materials so that it's obvious that in a GPU driven pipeline you can support well, materials is the wrong word, maybe textures, but like have a sort of full pipeline where we can open a scene, like a real production scene like San Miguel or Amazon Lumberyard Bistro or something, and render it, right? So we will start moving in roughly that direction, and our like next set of steps will be still completely disregard all of the texture stuff that we might want to do in the future, but I want to start doing a more complex sort of rendering pipeline, right, where includes occlusion culling and actually includes multiple types of meshes and all of that. Today is kind of a preparation for that. I think we'll get into a lot more of that next week. But right now we don't have a depth buffer, so if we wanted to do occlusion culling, it's not clear how we would do this exactly. We don't have a perspective camera, so that's weird, right? And we will start by adding these two things, and then we will look at switching the rendering that we are doing. Right now we are submitting for like 100 meshes, right? We are submitting 100 draw calls, which these draw calls are pretty fast because we basically don't change state between them, we just submit push constants, and that's fast. But we should be able to make this more optimal, not necessarily for 100 draw calls, but if you imagine simpler meshes so that we are not as bound on triangle count, but if you imagine like 10,000 of them or 100,000 of them or whatever the case may be, then we should move all of that stuff to GPU, right? But our first our first goal today is depth buffer and then projection matrix, perspective projection matrix, and then we'll have to change the culling a bit to work with that. And in general, sort of start moving from the sort of 2D world that we are in right now, where there's orthographic camera and no depth, to the 3D world with perspective and depth and stuff. So that is the plan. Hello, people on chat. So let's start doing that. So we'll start simply by adding depth. Now, the way our code works right now, and we've done this like on one of the first 2 streams, is whenever we create a swap chain, we create a frame buffer that already assumes that we aren't gonna use depth. And also there's an extra space here. Why? So that has to change. However, I don't want to bind this stuff too directly to the swap chain, because the other thing in the production renderer, the like data that you render to the main frame buffer, like not main frame buffer, like the scene frame buffer, I guess, isn't really the same data that you will be displaying to the swap chain. You might use HDR. I mean, you probably do use HDR these days, right? So it might be a different format or different encoding or whatever. You might use MSA if you aren't using TA or something like that, in which case you have to have multi-sampled targets, etc. We probably will not do MSA for now, because I'm not sure how it will interact with occlusion culling, but after we do occlusion culling, we might do MSA. So because of all that, I want to sort of restructure a bit the way things work. We will not create swap chains we will not create frame buffers with the swap chain anymore. We will just create a frame buffer, a render pass, and like a color and the depth image that we render to. And then after we render, we'll just copy from the color buffer to the swap chain buffer, and that'll be that. So it's slightly less efficient in the sense that there's an extra copy step, but again, in a production application, instead of this copy step, you have some meaningful workload that does tone map or MSA resolve and or post effects chain. So it's kind of correct to do the things like that anyway. And it also will slightly simplify our swap chain stuff, which might make it easier to like move it outside of this source file. Might make it easier, and in general we'll clean things up a bit. So that's the current plan, right? To get to that, I need a way to create an image, because right now the only textures or images in Vulkan parlance that we are using are created by the excuse me are created by the swap chain itself, but we kind of need to create our own. So let's do that. Let's first build our code and debug. Let's make sure it's validation clean. We are running fast enough in debug with 100 meshes, so we don't really need to disable anything. So we'll just run in our usual workload. So we covered buffer creation at some point on stream. Texture creation is basically very similar. I will need an image view and an image. And I'm wondering if I should, let me see. Yeah, you know what, why not? Let's just create. Oh yeah, we'll need them. Yeah, okay, yes. So we'll just create. We'll do the same thing, roughly speaking, that we've done with buffers. We'll create an object. We'll call it image. I'm sort of used to calling these things textures, not images. Image is a more correct name, I suppose, maybe, or maybe it's really the same, but for consistency, with the Vulkan terminology, we'll keep calling this image, but we'll have to bundle the image view because we kind of need this for rendering to the image anyway. And for now, every image that we create will be allocated in a special memory block. And this is again pretty similar to the stuff that we've already done. So let's see. Oh, the problem is, right, there's like creating an image is way more complex because there's a billion parameters. Okay, that's fine. So for now, basically, it will be simple. You need width, height, and format. We do need usage flags. I do not know image usage. Yeah. We don't really need. We'll basically assume for now that the image data. Yeah, we'll assume that the images always are in the GPU memory, and yeah, and we don't really need like to read out data from it or whatever from the CPU, so we don't need to specify which memory like sort of flags we need. Alright, so now that's the usual stuff. It's kind of boring. I'll breeze through that to the extent that it's possible to breeze through that, because you need a lot of flags as usual and things. Let's see. We don't really care about any of this for now. Oh, sorry, right. For now, we'll assume that images are 2D. Seems like a safe assumption. Format. Extent. No MIPS. No ray textures. Key simple count. Yeah, no multi-sampling. When you create Vulkan images, you are supposed to specify tiling mode, but there's only really one value that you should be using. So I won't really go into that. Now, yeah, okay, that's fine. Okay. Do I need to specify? I hope this is just for sharing. Oh, and the initial layout. Oh, but initial layout cannot be. Okay, yeah. Okay, I'm not going into too much details for this stuff. It's not terribly interesting right now. It might be sort of interesting when we start creating textures and uploading textures and stuff. But no, wait. Okay. So there's that. So yeah, memory flags will just say it's device local. Memory property device local bit. What's the flag? Yeah, memory property. So then we allocate the memory. Then instead of bind buffer, we have bind image memory. Presumably, yeah, same thing. Device image. Don't need that. And then we need to create the image view, which we won't really need this function separately because the swap chain. Yeah, for now we will just copy that stuff here. Oh, but I see. Okay, yeah, fine. We'll keep the function. So let's just fill these out. Device image format. And then let's have the destroy function similarly to the buffers. Don't know why I free memory first and destroy buffer later. It's kind of odd. Doesn't really matter, but it's kind of an odd sequence. So let's fix that. All right. Oh, I guess I technically allocate memory after yeah. It doesn't really matter. The order of destruction doesn't really matter in almost all cases, or maybe all cases in Vulkan. What is more important when you destroy an image is to make sure GPU is not using that, but we will handle that. So when we create an image view, and the only thing is we need to specify this aspect, which for depth buffer cannot be color, it should be depth, right? So let's pass this here. Mask. And we can pass this in, but also we can infer the aspect from format. So maybe we should do that. In fact, we could have done this inside the create image view. Maybe let's do that instead. Yeah. So there's a few depth formats, but we basically we'll be only using this one. So in this day and age, you should be using floating point depth buffers and reverse depth, which is what we will be doing today. Like, this aspect mask is a bit more interesting than just depth or color. Like, if you have a depth stencil buffer, you can have 2 image views, one for depth, one for stencil, or 3 image views. But we don't need all of that for now. So now in theory, we should be able to create like a render image or 2 of them. Let me see. But and remember, so this swap chain resizes things for us right now. Well, we sort of have to recreate it, I guess, in this function, but it resizes things for us, so to speak. We will not have this luxury, so we'll have to recreate the images ourselves. And this is encapsulated in this function, which is not great. Okay, that's fine. It's fine. Let's just, for now, should I do this? Oh, the swap chain will have width height. Okay, yeah, never mind. Yeah, so we'll just return a boolean here, which will be true if we resize the swap chain. And then if we resize the swap chain, we'll like recreate some stuff, right? All right. So we'll need to. Oh, and we'll also need a frame buffer. Right now, the swap chain manages frame buffers for us, but we'll need to create one ourselves. it doesn't really matter where we do this. I guess let's just do this here. So we'll have a color target, I guess, and we'll do create image, color target, device, and you know, all of the usual stuff. In fact, maybe to make sure we aren't repeating this code, let's just say that if we had to resize the swap chain, or if the target, I guess, image wasn't initialized, then we'll recreate them. So if there was a image, then we'll need to destroy it. Same for depth, and we'll need a frame buffer. Target frame buffer. So for now we'll just use the same formats that we have been using, which is this and this. But we are now creating a depth buffer, and it wants something else from us. Right. Yeah. So we have to render into the color buffer, but also we will be copying from the color buffer into the swap chain. So we need to say that we can image usage transfer source. Yeah. And depth for now we'll just leave alone, so we only need to render into the buffer. And we need to create a frame buffer. Right. And for now, let's just ignore the fact that we have a depth buffer so that we don't have to plug it in immediately. Image view width height, right? Swap chain width, swap chain height. So then, instead of rendering into the swap chain frame buffer, which we still create for now, this, right, we will render into the target frame buffer. So now it becomes slightly complicated. Let's see. We don't need to transfer this guy here. We'll have to do this later. So we'll move this here for now. This is not quite correct. Oh, but I guess alright. So render begin, we need to transfer, I guess, both. Let's ignore this for a second. It will be easier that way. And then at the end we will do vkcmd copy, and I'll need some barriers here. It's just every time you need to write barrier code, you need to think really carefully about what the specification should be, and then hope you got it right. So I want to first write the code that maybe works without validation. Yeah, so after we have rendered the image, We just need to copy the color target, and it, oh, yeah, but, okay, yeah. So validation layers will be very unhappy right now, because I have to do this. And then destination, which is swap chain images, image index or something like that. Why is IntelliSense not picking it up? Yeah. So we just need to copy the entire image. I think we need to specify the number of things somewhere. Yeah, the layer count. And then extend. So I will need barriers here around all of this stuff. Let's just YOLO this. I mean, I'll get validation errors, but I'll get other validation errors. Oh, copy doesn't work because copy cannot reinterpret the formats. Okay, yeah, that's fine. So I guess for now we will just create the target with the same format that the swap chain uses, which is like swap chain format or something like this. Is there a swap chain format? Okay. IntelliSense stopped working for some reason. Right, and when we create the swap chain, we are now copying to the swap chain image instead of rendering directly to that. So we have to specify, oops, somewhere, instead of color attachment, we need to say, hey, we will be copying into this image. And now we have layout transitions that don't, oh. No, we have more things to clean up. Oh, I see. Flags, right? We were not filling this. No, wait, hold on. Error message could have been nicer. Maybe. I don't quite get it. Hold on. What does it want from me? Am I just not specifying any usage flags? Oh. Wait. This is the swap chain stuff that started breaking. But we didn't. Oh, right, yes. We can't create an image view for the swap chain now because we aren't specifying color attachment. Yeah, okay. I will clean this up in a second. Remove color attachment. Alright, now we have image layout issues. that we need to fix, but let's see, maybe our code works at least. Okay, now the code works. So now let's fix image layout issues. And now I need to think about all of these barriers, beautiful barriers. It's kind of interesting that there was no error when we started rendering. Maybe it automatically transitioned, but maybe it's simpler. So what I definitely need to do, I'm not sure if I need the barrier between the before the begin pass now. I forgot. What I definitely need to do is that after I have rendered to the image, I need to say, hey, I want to transition the image that I have just rendered to from the layout that it was in, that was optimal for rendering, to the layout that is optimal for transfer. So that's the validation error that we got here. And also I kind of want to do the thing that we were already doing sort of for the swap chain, where we said we previously said we will start writing from color attachment to this, but now we are saying we will start copying to the swap chain image. Oh, and there's another bit somewhere that I have to change, I think. No? There was another weird... Oh yes, submit. Yes, okay. Alright. So there's like a bit of arcane magic here. Just ignore it. By the way, on some architectures, I would imagine that it's not very optimal to copy things into the swap chain images, but it's sort of a temporary thing. We might remove this later. So we are saying that for swap chain, we will start to transfer right, which means copy to right into that. And we need a layout stage that is transfer destination optimal. And then for the color target that we have just rendered to, we used to do a color attachment right to that. And what we need to start doing is transfer read, because we are copying from that. And we need to transition it from the image layout that it was in before, which is color attachment optimal, to transfer source optimal. And note that I am doing two barriers, or I am trying to do two barriers at once. Let's see if it will actually work out. So I need a source stage, which is attachment output, which I think is correct. And the destination, which is basically transfer, which I also think is correct. And then we need to specify all of them. Yeah. And this is not render begin at this point. This is like copy begin, right? Or it's just copy barriers. Let's just call them that. Wait. What is it doing? After copy, we used to have this barrier that we still need, which said, hey, swap chain we need to start being able to present from this, which is this guy. But instead of color attachment, we now are saying it used to be in transfer to destination optimal. And we used to do a transfer right. And this guy has to be transferred bit. And instead of render and barrier, we'll call this present barrier, because this is what it's doing. I don't know, I think that's correct. Let's see if validation layers agree. They do not. Oh yes. So this is the barrier that I thought I needed, but I didn't see the error, so I was confused, but I guess the error just got delayed. So yeah, we do need another barrier, which was render begin barrier, sort of. So let's do that. And we'll need to do this for both color and depth. We are not using depth like at this second, but we will start doing this like super soon. So let's just say, yeah, so color attachment image, we don't care about the contents of the image, but so we can say that we don't really care what the axis even was, I think. I don't think any of these are important, I want to say. But we do want to say that we want to completely disregard whatever was in the image before, which is image layout undefined, and we want to start using attachment optimal. And same thing for depth. So let's just do this now. No, depth, stencil, something. Depth, yeah, this guy. And I don't know what this should be. This or something? I'm not sure. And output stages should be, I think, both pipeline stage. Wait, hold on. I don't remember, is it late fragment tests? Let's see. So it looks like this stage is defined as the stage I need this stage, I guess. I don't know. This stuff is hard. I'm not sure if I need this or both or neither or what. Let's assume for now that I need this. As I was saying on stream before, one of the big issues with Vulkan is there is no validation for the stages. Yeah, okay. Oh, right. Right. So I guess this should have aspect mask. Okay, let's just pass in an aspect mask. Aspect flag. So because of this, it's really hard. So validation layers are correctly validating these guys, which is really nice, but they don't really correctly validate these guys, which is not really nice, which means that we might have errors. Like, in fact, it is likely that we have errors that we just don't know about, which doesn't inspire confidence, but you know. And yeah, we need to destroy stuff. So we need to basically say, it's basically this code. Maybe we'll want to move this to some struct with some extra functions later, but I think for now this is good enough. Okay, so we don't have validation errors anymore. Let's remove the swap chain stuff that we are not using now. In particular, we don't need the views, we don't need the frame buffers, which is nice because our swap chain becomes simpler. so that's cool. Right, so basically just doing that. Don't need to destroy them. And then we left this to do comment just now. No. Oh, this was a GeoSlang bug. We have filed this, but it's not fixed yet. But I'll leave the to do comment for now. So we don't need this. Does resize work? Seems to work. Okay. Now we can start using the depth buffer that we have just created. To do that, we need to, let's see. So we need to specify the depth in the frame buffer. Right now, when we create the frame buffer, we only specify one view. So we need like color view, depth view. Okay, so then when we create a render pass, right now we are saying there is one attachment that has that is cleared, and then we store the contents to memory and then some other things. So we need to expand that to have two attachments. Oops, wait, hold on, where do you go? One will be color and one will be depth. So when so we need to clear as well. So this is a bit that might seem suboptimal, but I'll leave a note. This is so when we don't use the depth buffer after we have rendered, right? Well, or I could just remove this and then we can, yeah, you know what, for now we just say store up don't care. Like we will need the depth buffer when we start doing occlusion culling. But we don't do occlusion culling right now, so I guess there's no point doing that. So depth, stencil, there's that, there's that. P depth stencil attachment. Why is it attachments if there's only one? You can see that we are oh, it's this guy again. You can see that we are specifying like a lot of these bits all over the place every time. Like this is, wait. No, not read only. Damn it, IntelliSense, hold on. This guy. Right, so we have like this guy 4 times in our program. This complexity is there because you can use a more complicated render pass that describes your entire rendering sequence. But we don't need to do that right now, and we won't really be doing that on stream anyway. And I don't agree with this idea in the first place, so we will not be doing that. Okay. All right. So now we need depth format. Let's do this. So that we don't, I guess we don't, yeah, you know what. We have specified this. Now it's probably nicer, like if we ever want to change the format. It's probably nicer. It's still specified here, but it's fine for now. Yeah. And now we need to specify, and I think validation layers will tell us that. No. Oh, right. We have 2 attachments, and attachment 0 is the color and attachment 1 is the depth. So this is what the 0 and 1 refer to. Right, and now it's telling us that when we begin the render pass, we are specifying the clear values, but we have two things that we need to clear now. One is color, one is depth. Okay. But I guess we'll be using reverse Z. So for reverse Z, the far plane is at 0. So there's that. How do I... This will not work, right? Yeah. Oh, but I can do at least this. Alright, and then I don't need... So let's do it like this. This is a C++ 11 feature, but it's super handy in this case. Okay. Oh, wait. Hold on. Hold on. What I'm doing. So we need clear values, really, right? And then we need clear values 0. And then clear values 1. And then this. Okay. Now you cannot see the difference, but we are not even using the depth buffer right now, so that makes sense. Should I? Let's disable backface culling briefly. And we should see, yeah, so this is what happens when you don't have a depth buffer. When we do backface culling, you can see that some parts of the kitten are like sort of bleeding through. And when we switch to the traditional pipeline, you can see that most of the kitten is bleeding through, right? So like right now you're seeing the back faces of the kitten. To not have this problem, we need a depth test. So yeah, I think right now the depth test that we are doing. Now let's just do this correct. Let's just do this how we will do these things for perspective projection. And that's it. What's min depth bounds? Oh, depth. Oh, okay. We don't need that. What is this thing? Don't need that either. So yeah, all we want to say is that we have depth stencil. Oops. We want to enable the depth stencil test, depth test rather. We want to enable writing depth values, and then we want to compare them with a greater than. And if you've done computer graphics before, you may be thinking, hey, don't you pretty much always use less than? But we are doing an inverse depth test because we will want to store far plane at 0, because we'll use an inverse Z projection matrix. So that is why. And then I guess in the shader right now we are taking the depth, the Z value, and then multiplying it by 0.5 and then like adding 0.5, which means that it's not reversed essentially. But I suppose we can just do this, and then it will be 0.5. Yeah, I think this will work. And then we need to do this here as well. Okay, our depth test worked, right? So now we are rendering still with orthographic projection, but with the depth buffer and the depth test, which means that we can have the like pixels that are behind other pixels rejected for us, right? Okay, cool. So this is the good first step. Now I can, I guess, re-enable backface culling. We only disabled backface culling to make sure that our depth test definitely works, but now it's clear that it does, so we can restore it. Okay, I think we are done here for now, and now we need to do perspective camera, but then I'll submit this first, because this is a good step to fall back to if our perspective camera work just explodes somehow. I don't think we did anything that we would want to not do in the future. Like, I don't think we have any to-do kind of stuff. I think that's good. Alright, so let's look briefly at the diff. And we've changed the shaders a bit, but that'll go away with perspective camera. Alright, so this is day 10, I think. Add depth buffer support. To do this, we are now rendering things into a separate color depth, into separate color depth images. This will I mostly did this so that I don't have to have like two frame buffers for swap chain, but this might help us in the future if we decide to do MSA or HDR or anything like this. This is not a stream about sort of PBR and HDR and all of that, but who knows, maybe at some point we'll actually go there. This is mostly a stream about other things like GPU rendering pipelines as opposed to shading and lighting and stuff like that. Alright, so now we need perspective camera. Yeah, so the goal was to include all of the parts of the kittens that aren't showing using a hardware depth buffer. So, so for people who don't know what reverse Z is, you should read up on that. There's an article by Nicholas, I think, Gelmot, who has a bunch of links. So like you might want to read that kind of stuff. But all we want really from this is like this formula. So we want to start to move in 3D world, right? So we want to start rendering things in 3D with like translations in 3D space, rotations in 3D space and stuff like that. And then we will want to use a projection matrix to have an actual sort of 3D scene with perspective. Now, for now, we will assume that there is no view matrix. So that camera is at 0, 0, and points in, who knows which direction Z points to here. Might be minus Z. But like no view matrix for now, we can't like really move the camera or anything like that. But we would like to have a projection. So yeah, reverse Z basically has an infinite far plane but finite near plane. But this value can be pretty small. So like in this case it's 0.01 and it should be fine. When you have reverse Z with a floating point depth buffer, you don't suffer too much from the depth precision issue. Z fighting gets way better. We've implemented this, basically every game should implement this by now. We've implemented this in Roblox like a year and a half ago maybe or something like that. And it's been really good because with this matrix the error that you get in depth precision is roughly equal, if you use floating point depth buffer, is roughly equal across your entire Z range, which is really nice. So this needs basically And this matrix depends on the field of view, which is just constant, right? Well, it doesn't have to be constant, but for us it'll be constant. But it also depends on the aspect ratio, which depends on the window, right? So we have to pass this to this shader. So we'll just pass this projection matrix, but this projection matrix is really like 4 floats. And so this should really be something like, if you have a position, then it should really be position x times this f over aspect, position y times f, position z, let's see, I don't know unfortunately if this thing is column wise or what, but I think it's, yes, it should be position w is basically minus position z in this framing, and then position z is position, wait, oh, yeah, that sounds about right. That sounds about right. So this would mean that when z is in front of the camera, it should be negative, for this guy to be positive, and for this division to work out. Because this is, I guess, a right-handed matrix. I don't like camera spaces that are like this, so we will do this. And this is just our perspective transform, right? So really what we need is we need to have these like 3 floating point values in the shader, and then in the shader we can do a perspective transform. For now, we will just, this is not a forward-looking solution, but to take things, wait, where am I? Or I guess we can just add the entire matrix, because at this point it's just a buffer. Yeah, you know what, let's just create a buffer. Let's just do this right. So we need this function. Should I just use GLM at this point? Should I use GLM? GLM? I mean, we'll need GLM anyway. Let's just use GLM. I wanted to start using a math library, and I looked around. GLM is the obvious choice because it's close to GLSL and seems like a nice library. It's a bit bulky for my tastes, but I didn't really find anything else. So I think we'll just use GLM for now. So it is on GitHub. It's like a really popular project, as you can see. Where is the, yeah. So let us add it as a submodule. Oh, interesting. The other links that I have are, okay. Yeah, you can see it's like 60 meg repository. It has a bunch of tests inside it or something like that. Oh, why did... Okay, no, it's all good. So now that we have GLM, well, we need to configure and include paths. Obviously, GLM is a header-only library as far as I know, but you need to add it. I guess you just need to add this folder. Wait. Oh, what am I doing? So yeah, in this giant list of things, we need to add essentially this. I guess the order doesn't really matter. Yeah, we can put it next to GLFW. Looks nicer this way. Okay, so now in theater we can start using like matrices and vectors and, you know, the privilege of the modern world. On the stream we try to use third-party libraries that save us time as long as they don't As long as they don't, like, as long as they aren't related to Vulkan per se, right? Like, we won't use some like Falcor or something like this, which is like a rendering framework or the Forge or whatever, but we will happily use other things like GLM that just save us time. So let's just include something. I'm wondering, hold on, backtracking a bit. So let's see how heavy the entire GLM is. So that's not that great. It's kind of noticeable. It's not as bad as the Vulkan HPP, but it's not too good. So let's for now just add, we'll want to use a vector. Is there quaternion support? Oh, there's no quaternion support. Oh, but it's here. This is kind of odd. So we'll want quaternions, vectors and matrices essentially. What am I supposed to include? What is GTC? Oh, I guess I just need this header, right? So it's GLM ext quaternion float, and then we'll need a matrix because oh wait, so that's roughly the same amount of time as the entire GLM header. Oh no, I guess, okay, maybe this is fine. Anyway, yeah, so this will do for now. The reason why we need the quaternion is we will have to be able to move our kittens in 3D space, but also rotate them in 3D space. And for this we need the rotation, and rotations can be represented with quaternions. And I like quaternions more than matrices, so there's that. Is that just an ls for, yeah, okay. So let's just call this view projection, I suppose. Even, no, let's just call it projection for now. Yeah, we don't have a view matrix. So we could pass the projection matrix with constants, with push constants, but right now every mesh that we have has a sort of separate push constant block, right? And uploading the matrix for every single one of them seems wasteful. So I suppose we just need, or I guess the other thing we can do is yeah, okay, you know what? Let's just, to get something on screen, let's just be really wasteful. Should not be doing these things, but it's fine for us for now. Especially because this matrix is really for floats, but I want this to really be view projection, and then it's an actual full 4x4 matrix. So that's fine. Alright, and then we need to compute the matrix, which we will just steal the code from the blog post, except that we will flip the Z order around. So let's just call it projection of y, radians, aspect. This is not quite like the coding standard is different from what we used to. So let's do that. This should be tan f, not tan. And this should be 1. So that's, it could be that GLM itself has a function to do that, but So the field of view will, let's just call it 70 as well. Was there a GLM like radians? Oh, nice. Okay. And aspect will be float blockchain width over that, and then linear, you know, sure, it doesn't really matter that much. So that's good. So this is temporary, this will move out. And the other thing that we really need is we kind of need like a full 3D position and scale and rotation, right? So let's just do this. The W component will contain the scale. I don't remember if I can do this or if it'll break the... Let's hope it'll work. Let's hope it works. And then we need to do... the correct term is not rotation, it's orientation. Or I guess here we could say translation, and then it'll be rotation, but position orientation. Okay, so let's do the same thing here. Is Vec3 like aligned to something? Doesn't look like it. Oh, who knows? Okay, let's try this. I'm not sure if the data layout will match. But hopefully it will. So for now, let's just ignore the the orientation. And for position, let's just say that the Z, all kittens are in front of the camera at some distance, and then at some position, and then we'll change this later. I'm like worried that at this point we'll just have the mesh not render, and then since we don't have a debugger working, it will take us forever to figure out why. So for now I want to be conservative. So we multiply by scale on all axes now. So this is just that, I suppose, right? And then we add the position, and then we ignore the rotation for now. And this is our Vec4. And then instead of our weird sort of projection but not quite matrix, we just do a full matrix multiplication. I don't know if the order here is correct, because I'm not used to working in GLSL. But who am I kidding? Even if this was HLSL, you can never know if the matrix multiplication order is correct. So this is what I was worried about, right? We have nothing on screen. So now we'll have to figure out why. Did we fill? We basically filled everything. So the first hypothesis, as usual, is, hey, projection matrix multiplication is... Oh, okay, cool, all right. See, I never know what order things are where. I guess this actually makes more sense. Yeah, this is more how I'm used to thinking of linear algebra. But in HLSL, sometimes the convention is the opposite, but sometimes it's the same. But yeah, that actually makes sense. Okay. All right. So now we probably have a camera, right? Let's try to move the kittens closer. So instead of like 10 units of space or whatever, they will be closer, right? And we can like scale them differently, and hopefully these things work. So to make something that is more interesting, we want more of them. And then I kind of want to just fill a volume of space with randomly generated kittens. And we'll just do this every frame for now. Or actually, we can move this. Now we can move this. Oh, we didn't test if. Hold on. I am jumping ahead. Hold on. Alright, let's see if the aspect ratio stuff works. Right, so yeah, so if we resize the window, now we see a wider view, which is expected. And I think also maybe our... Yeah, awesome. Alright. The other thing that we see is that our cone test doesn't work anymore, which is super expected. You see that when I switch between the rasterization pipelines, on some kittens, on the kittens that are sort of to the right, some of the clusters disappear, right? So this is with mesh shading on, you see like extra holes sort of right on the side, and with mesh shading off you don't. This is because our cone test was correct for orthographic projection, but it is, oh, actually this is because of multiple factors. Yeah, but now it's like super incorrect, because we are not including yeah, we're not applying the transform to the cone, but the transform right now doesn't contain rotation. So the bigger issue is basically our test right now works for orthographic projection but doesn't work for perspective. So we need to fix that. So I don't want to fix this just yet because I want to generate like kittens in a different pattern. So let me first move this thing out, because you know I'll be using some trigonometry here, and it's like we are running in debug, and why do this every frame, right? So for now we will still fill the projection matrix in every draw call, but this thing will go away soon, because it'll have to move to a different buffer anyway, for reasons that will become more obvious. Hopefully on stream. We are doing reasonably well on time, so I think we'll get to the draw indirect stuff. So let's check if that still works. So now I want to do something like, let's just use the C random number generator is not a good random number generator, but C++ random number generator has a crazy horrible interface. And I don't quite want to use that, kind of despise it, honestly. So yeah, let's just for now say, hey, that, I mean, rand is a really bad random number generator. Maybe we'll just get PCG32 or something, because that's way nicer than anything that C++ has right now in standard library anyway. So yeah, so this generates a random number between 0 and 1 inclusive, and then we'll just say, hey, can you sort of spread this around? And this will mean that there are some kittens that are behind the camera and there are some kittens that are in front of the camera, which is perfectly fine. So let's fill a volume, say, I don't know, 100 by 100 or something. So it's like times 100 minus, well, let's fill a radius of 100 units, whatever our units are. Let's do this. I don't know if we need to scale them, but let's see what happens if you just do this. Oh, they're really far away now, right? So I guess 100 is a lot. Yeah, it's a relatively large volume, right? So A, we need more of them, which is just as well. All right. B, let's push them closer to the camera for now. So maybe something like 40. All right, so that's kind of what I wanted. and we are starting to run pretty slow. It's like 7, but we are pushing a lot of triangles right now because we are running 10,000 kittens with 29k triangles each, so that's a lot. Times 10,000, is that? So that's like 290 million triangles. Yeah, so that's clearly a lot of kittens, right? Let's be slightly more conservative for now, so that we are running at, well, I want to have the GPU time be like in a reasonable sort of range, like 4 milliseconds seems okay. Oh, and we're spending a lot of time on CPU, but this is because we are running in debug with validation layers enabled. I think if we run in release, we should be able to run at 60 FPS. Because we remember we are still doing like 1 draw call per kitten. Yeah, so in release we run at 60 FPS. So 4 milliseconds is, I guess, okay. Right, now we have this problem, right, that is super clearly visible, where the cone culling culls away stuff that it should not be culling away, right? I want to commit this because we have a thing going here, but we aren't using the orientation yet. So maybe we should do that first. Let's see. So I want to have, I've never used GLM quaternions before, and I barely used GLM before. But I'm hoping that there is some function and that will do something for me. Oh, this only includes the type itself, I see. So then you have to have like this guy or something like this. But why does it take... Guess that's fine. Should I just include like the entire GLM? Oh, but it doesn't even... I see. It doesn't help me. It doesn't include extensions. Okay, fine. I will just include headers one by one. Yeah, so I want a function that gives me a quaternion, but this just is boring, right? Oh, it normalizes the angle. Oh, the axis rather. And then it... So that's cool. GLM is like heavily templated, which I don't love, but again, I don't know. If somebody has a suggestion for a math library that we should use on stream instead, please write it in the chat or in the comments or something, and you know, we might switch to that. Like, my big gripe against GLL is there's so much template stuff everywhere. It's like hard to read this code, and it's, yeah, not a fan. But on the bright side, it seems to work. What does the default initialization... Like, this is the problem, right? So like, here's the question: what does the default constructor for the GLM quad do? Who knows? GLM default, I guess this means it doesn't do anything. So what other constructors do we have? So we have this one, which I guess... Oh, and there's also other static members now. Okay. Yeah, like for people who know how quaternions work, I guess this is fine. But like, for people who don't, this is a dangerous interface. Alright, so I guess, oops. So I guess that's what I need to do. And then angle. So float rand. Rand max. Let's say that we need a rotation angle up to 90 degrees. And then the axis. And then it looked like the function will normalize the axis for us, which is maybe a tiny bit weird, but let's use that. Okay, and now let's actually use this data. To do that, we need a function in the shaders that transforms a position, like rotates a position by quaternion. There is no function like this in GLSL, so you'll have to write it. And I don't remember the math off the top of my head, and also there's no way I am deriving the math off the top of my head. So let's steal this. I'm hoping GLM has a good implementation. So let's steal it from that. Squat, cross, rotate. So yeah, so I need this guy that rotates a 3-component vector by quaternion. So I guess it's in quaternion INL. Thank you, GLM. You have been incredibly helpful. So I guess I need something else, like one of these guys. Alright, you know what? So we don't need this anymore, we don't need this anymore. Right. So quaternion, like rotate vector, vector by quaternion. I just want, it's like 2 lines of GLSL code. I just don't want to mess it up, right? Because I don't want to debug like quaternion math right now. Yeah, this is what I want. This is the thing that I wanted. Yes. Okay, so that's good. So let us, let's just like put this function here for now because there is no other shared header. Call it rotate quad or something like this. So you pass it a vector and you pass it a quaternion and then it returns a transformed vector. So that's the only thing I wanted. Oh, back 4. So you can see it's like pretty simple, right? It's like 2 cross products. I believe this formulation comes from an NVIDIA math library from like 20 years ago or something. So we will just use that. So when we transform stuff before, our scale is uniform, so it doesn't really matter where we do this. But let's just say that here we say rotate quad, position, mesh, draw, orientation. And then same thing in the other shader. Rotate quad, position, mesh, draw, orientation. Okay. Our kittens are rotated. Now it's pretty obvious that our culling just doesn't work at all, but this is because we are not taking the transformation matrix into account. at all, right? Because we need to be rotating the cone at least by the same rotation, but then also we need to take care of the perspective stuff. So let us do that, but let us first, let us just do that, and then we'll submit all of that. So cone culling right now is naive, right? It assumes that the first thing it assumes that the cone is already in world space, which it definitely isn't. For us to fix that, we need to use the same data, and we wrote code on stream yesterday to help us manage this, so we can just paste this code here and we get access to this guy. So we need to read that transform, and we need to apply it. So there's three parts: there's position, scale, and orientation. We aren't using scale right now, and we probably should, if only to help us make sure that our code works, right? So let's just say that the scale will be a value from, let's call it 1 to 2, right? Not too aggressive. I guess some kittens became smaller. I don't know. It's hard to know. We should really like spin the kittens by adjusting their orientation every frame. But actually, we'll do it later. We'll do it to make sure that we definitely have the cone tests correct, probably. But yeah, so now some of them are scaled. It's not very obvious because, right, the range of scaling is really small. Like if you wanted to make a larger range, we'll do something like that. But then some of them, does it even work? Did we forget to do this? To multiply this? No? Are we even using this scale value right now? What's going on here? Oh. Is it the thing that I was worried about, where the layout is now actually different? We are using the scale. This is suspicious. I'm worried that somewhere, maybe on C++ side, maybe not, our memory layout diverged, because it doesn't look like scale is working. So let's look at the mesh draw structure, and let's not look at this in hex. 96 seems correct because it's 64 plus 32. So and 32 is the correct. There's two vectors there, so this seems fine. Right, so yeah, something is up, I think. Maybe on GLSL side it actually doesn't put this float where we want it to. Let's see if this is true, because I kind of expected the scale on the C++ side to make a difference, and even if we are crazily aggressive, unless this math is just, no, but this should be the correct math, right? So we should have scales right now that are just obnoxiously large, right? Wait. Oh, okay, never mind. C++ strikes back. Never mind. Okay, it's still good, scale works. Okay, yeah, we were doing integer division instead of floating point division. Okay, so now this looks sort of different from the previous stuff, because some of the kittens are larger and some are smaller. And now we need to fix the culling to work, right? Which should not be very hard. So, culling. I want to submit this first because we'll need extra mesh data and things like that. So day 10 rather, implement perspective transform and 3D positioning, right? Each mesh has a position, uniform, and orientation. We are doing full perspective transform with infinite foreplane and randomizing the positioning of meshes. So that pretty much is what the problem is, right? All right, so so there's two parts to that. The first part is just sort of stupid, right? We are just like, we are now rotating the kittens, but we are not rotating the cone. So that's trivial to fix. We just need to say rotate quad cone and then mesh draw orientation, right? Really, are we not including? Oh, yeah. Oops, hold on. So, yeah, let's just say that. Right. Okay. So now it's better, right? We are no longer missing like half of a kitten in some cases. However, you can clearly see that even though in the distance things seem correct when I flip back and forth, right? Mostly, but on some close kittens the difference is like super apparent. So this is because we are still doing the test that is correct for the orthographic projection, but it is not correct for perspective projection. There is two ways to fix that. And one of them is, both of them are supported by the Mesh Optimizer library algorithm that we have switched to yesterday. And we can kind of try to use both of them, if only to make absolutely sure that they both work, which I think they do, but let's see. So both of them require extra data per meshlet. So right now we only have one vec4, but we need extra data for this. So let's add extra data, right? And then let's see which test we like more. I think I know which test I like more, but I want to make sure that it all works perfectly and stuff first. So first, let's just mirror. I guess vec3 keeps this aligned anyway. So the extra pieces of information that you can pass are there is a bounding sphere for each meshlet that we are already computing on the CPU side. We just aren't storing this data that you can use to fix this test. And the other thing that you can use is the cone apex. And let's just add padding. I don't think we'll need this necessarily, but just in case. And that also can be used to make the test conservative. They work in a different way. Again, didn't set up the drawing, like, I don't know where my surface is. But very briefly, wait, okay. Again, I'll just like draw with my mouse. So very briefly, so for a normal cone, basically what you can do is you can specify this point, which is an apex, and then you can do a conservative test. Or you cannot specify this point, but you can specify a sphere. Oh, well, this is what happens when I draw with the mouse. that has a center and the radius, right? And then you can adjust some math in the shader to make sure that depending on the distance between the sphere and the camera, you get correct testing, correct cone cull testing. And both of these methods should work. Both of them should be conservative. The apex test should be slightly more precise, but it's like really ever so slightly more precise. And the bounce test is slightly less precise, but the benefit of this is that you may want the bounce of a meshlet like center and radius bounding sphere for other reasons. For example, if half of the kitten is outside of the viewport, then maybe we want to do frustum culling, and then we will reject clusters before they get to the rasterizer, so we don't have to transform vertices on them, etc. And then we want to do occlusion culling as well. So we'll probably settle on the center and radius method, but I want to make sure that both work. So for now, let's just add data for both of them. And I plan to do a blog post on this stuff. Maybe. I don't know. I kind of want to do a blog post, but finding the time for a blog post is hard. Should we just use GLM here, I guess? So we have cone axis, cone cutoff, and then we have center and radius and cone apex and padding. And let's just fill these in. So center is I wonder if GLM has a constructor like this. It doesn't seem like it does. It's unfortunate. Is there something like that? No. Oh well. Let's be verbose and not make typos. Okay, so then we have cone apex. Oh, and I will want to switch between the culling modes to make sure that we're actually culling a reasonable number of triangles with both modes. But let's so first we'll check that both work, then we'll check that both cull away stuff, and then we'll pick one. It doesn't really matter, but whatever. And then we have switched this to vec3. Alright, so that should work, except that our code doesn't compile because we have renamed things. So this is cone axis and this is cone cutoff. So that's the same thing for now. We are not changing anything. Yeah, we are doing like test on the C++ side. Let's just remove this. So far so good. Same thing, we aren't doing anything differently. Now we can start doing things differently. So one variation of the test, and this is all, let's just, to make sure that I don't do things incorrectly, this is all, come on, wait, what's going on? Yeah, so this is all documented in the Mesh Optimizer library. There is 2 formulas that you can use, or it's like 2.5, but it's really these two that are interesting. So let's just make functions, right? So let's do this. Is this used later? We'll just compute all of them and then, you know, see which one works better. So this is our old function, right? So then the other function, requires an apex, cone axis, cone cutoff, and then instead of view vector, it requires a camera position. Our camera position right now is in 0, 0, 0 because we don't have a view matrix, right? So this will have to be passed to the shader later once we have a view matrix, but we don't have one now. And then there is the third one, which instead of the apex says there should be a center and radius, and then axis and cutoff, right? So it's probably almost valid GLSL code. Let's see, normalize cone apex minus camera position, cone axis. Okay, this is like valid GLSL code. Is this valid GLSL code? This is probably valid GLSL code, but it's slightly redundant because it recomputes. Come on. It recomputes this radius vector between here and here, but generally speaking, optimizers optimize this stuff away. So yeah, okay, this is also probably valid GLSL code. And then remember that since we now have like world transform for the mesh, we have to transform these things into world space. So for the cone apex, we just need to translate it and rotate it. Yeah, so for this we need to do a full transformation. So we need to do let's see, cone axis, right? So so we need to rotate the cone apex by the orientation, and this apex is a point in space, right? So then we need to multiply it by the scale, and then we need to add position. So it's slightly long, but bear with me, we will refactor this once we and the camera position is 0, 0, 0. So then for the center, we need to do the same thing for the center instead of the apex. So that's just that. And then we need to pass the radius, which should be mesh, let's mi radius times scale, right? Because if you grow the mesh, if like the mesh gets larger like 3x, every bounding sphere of every mesh that also should get larger 3x. So I think this correct. This seems correct to me, except this should say 3. And now we can look at, you know, wow, code not compiling. Messlets, no. Or cone call 2. This is 3, not 2. All right. So again, this is our conservative orthographic method that is conservative for orthographic, does not work for perspective. So this is the apex method. And when I flip back and forth, I don't see any pixels flickering, which should suggest it's basically perfect, right? Hopefully. And then for the method number 3, same thing, right? Nothing changes on screen. So you can see that these tests have, I guess, similar cost in the sense that you have to transform roughly the same amount of stuff in both cases. You have an extra multiplication here, which is not super important. And then here, this normalize and this length is roughly equivalent, because this is normalize is basically just computing the length and then dividing the vector by that. So this has a divide, this has a multiply, but then there's an add here. So it's like roughly the same computation wise, right? Between these two, it's not that much of a difference. The real difference is the cone apex is completely redundant information for any other test that you might want to do, whereas center and radius is useful for other tests, which is why if both work and if both call reasonably close amount of things, which I think based on my math derivations and experiments, they should call roughly the same amount of things, then you should probably use this one because you might want to use center and radius in for other tests, right? But if you only care about the backface culling, then you can use this one because this is more precise a bit. So now let's test that our culling code actually culls away things, right? So for that we do the usual thing where we flip the culling somewhere. Okay, so we have a bunch of things called, obviously, like it's hard to know how close this is. We can't, I will take a screenshot. All right, did it work? Okay, it did work. And then, so this was the, which method was this? This was the method number 3. So let's say so in a smaller font, if at all possible. No, paint, come on. Okay, then let's use method number 2. Okay, it still calls away stuff. Did I actually copy? I'm not sure. Let's do this again. Let's actually make super sure. Alright, so now we have like different thing in our clipboard. Alright, so that's method number 2. It should be, no. Paint, okay. And for completeness sake, I guess, let's look at method number 1, which is incorrect. So like it may call more things away, but even if it does, it's not like correct, right? Because it calls away things that should not be called. Is this stuff actually like changing? Yes, it's recompiling the shader, so it hopefully works. I'm just afraid that I will like do a comparison between like that the images will be identical, not because the math is the same, but because I forgot to oh, okay. Rebuild the shaders or something. Okay, it will be kind of more helpful if you save these guys. So let's save this. So this will be 1 PNG, this will be 2 PNG, and this will be 3 PNG. And we don't need this, we don't need this, and we can photos. Okay. All right. So this is a comparison between 1, which is incorrect culling, and 2, which is correct culling. I don't even know if it's more stuff culled away or not. It's hard to tell. It seems like it seems basically 2 culls away more things, which might actually make sense because some of these, like the cone culling test, if you assume orthographic projection, it's like so different on meshes that are close to the edge of the screen because of the perspective distortion. Like in the center, I would expect them to work roughly the same. Yeah, so like if you look here in this area, then it basically doesn't really change, right? Yeah. And then this is the difference between 2 and 3, right? So you can clearly see that in 3, there is a bit more visible clusters. Sort of, it's mostly close by, but in some cases it's sort of far away, which is expected. Again, as I said, the cone apex test is more precise. It looks from this picture that, you know, the difference isn't dramatic, which is consistent with my experiments, but the difference is there, right? So we will cull away slightly more things with the apex test. We can try to measure performance. I'm expecting that these delta is kind of small and it won't matter, but we can try to confirm that. So to confirm that, we need to go back to our normal culling mode. Right, release vsync. So let's see. So we are rendering, by the way, 23 billion triangles per second. But remember, some of these triangles, a lot of these triangles are off screen, which actually isn't that important because we aren't doing like frustum tests, but the rasterizer rejects some of the stuff a bit more efficiently. So, but it's still the case, even though triangles are off screen, right? With the old rasterization pipeline, we are getting 15. With the new, we are getting 23 billion triangles per second, right? I think if more kittens were on screen, the delta would be larger because we've seen a larger delta yesterday. But right now, yeah, this is what it is. So anyway, so with the mesh shading on, we are getting 23 roughly billion triangles per second, right? Yeah. And then this is with the test number 2, which is more precise. And we are getting, yeah, basically the same amount with the test number 3, which is what I would expect. The difference is not that dramatic, right? Because the difference is not that dramatic, I will keep the one that does not use the apex, because we want to have other types of culling, so the fact that we have a bounding sphere will help us in the future. So now let's just clean this up, right? We only need the apex, we only need the like center radius thingy. And then now we can actually use a like 8-bit representation for this, because now it feels weird to have 32 bytes dedicated to just culling data, which we will do. Will we? Yeah, which we will do. So right now our mesh-led structure is basically 3 16-byte values instead of 2, 1, 2, and 3. We can compress it to just 2 pretty trivially without touching this thing at all, which we will do momentarily, but let me first clean the code up. So we are only interested in this test. And then I want to like unpack this expression so that it's less scary. So we want vec3 center is this, and then vec3 cone axis is basically this. Oh, and I guess, yeah, like sure, like radius is this. Right, and then we can just replace stuff with the center. Oh, and then this is radius, and then this is cone axis. And I guess might as well at this point just treat this data. Apex. Oh, right, and then on the C++ side we don't need to fill this stuff. Whoa. Wait, no, hold on. This is not okay. Yes. Okay, good. The reason why we are now running at 17 billion triangles per second is because we have disabled vsync. I mean, enabled vsync. Disabled the disablement of vsync, which pushes the GPU clocks a bit up and stuff. So it's expected. I think it's fine. All right. So now when I switch between 2 pipelines, I don't see, we can do like an image comparison, but you know, between me deriving the math and I like sort of proving, I think to myself at least, that the math is correct, and us not seeing any obvious problems, I think this works. All right, so that's good. We have fixed the cone test. Oh, and I guess let's repack the data now to, yeah, let's repack this guy. so yeah, we'll just basically, I think we did this last time as well, but we basically can store access and cutoff components as 8-byte integers, and there's already, you have to adjust the tests a bit, not to test the values, like it's not just, hey, let me just store these things in 8-bit integers and see what happens. You have to carefully adjust the cutoff so that the test remains conservative, but the library already does everything for us, so we don't need to think, which is great. Nobody likes thinking, right? So yeah, now this data is 8-bit integers, so we have to do it like this. And then this is painful because damn it. Every time something happens. What happened this time? Oh, did I forget to... Yeah, okay. It's kind of high time that we like started using one struct so that we stop getting this crazy flickering things. But I don't want to do it right now because it's been 2 hours and I still want to quickly check if we can get draw indirect running without any effort. Alright, yes, we are still at like 23 billion triangles per second, so that's nice. So now let's submit this. And now our meshlet structure should be basically 32 bytes with, what is it, 6 bytes to spare, so we can store some other stuff there if you want. And in theory you can repack center and radius. It's slightly like you can't fit the entire thing into 16 bytes. It's slightly painful because you have to pack center in a very special way. So we are not going to be doing that, especially because for now it looks like performance isn't really affected by the size of the struct. Like we just moved from a struct that had both apex and center and radius and like everything, which was I think 64 bytes to 32 bytes, and we are still running at 23 billion triangles per second, so we right now are not really limited by the size of the struct, so we don't care about really tightly packing this. I just felt that it's like wasteful to not store the already pre-computed 8-bit integer data that we have, right? And now we have some space to spare for 32 byte boundary. Alright, so yeah, day 10 fix cone culling by using alternative formula for perspective projection. No. Okay, yeah, formula for perspective projection. Right, let me quickly, oh my god, there's a lot of stuff in chat. Why are there Roblox questions in chat? This stream has nothing to do with Roblox. So please don't ask questions about C-frame and terrain here. Thank you, Lape64. I'm glad these streams make people happy, because this is half of my motivation for doing this stuff is because I'm experimenting with technologies that I haven't used before, that I have always wanted to try out. Half of the motivation is, I guess that's three halves, is that some of the stuff overlaps with the Mesh Optimizer library things that I have wanted once again to do for a while. So the stuff that we do on stream actually benefits other people, because now again Mesh Optimizer has really robust support for cluster bounds and meshlet bounds, and also it has support for computing meshlet data, which right now is robust but not optimal, but it's really hard to make it optimal, so I'm planning to do some research on this later. So the stuff benefits people who aren't even using Welcome necessarily, by the virtue of us having to write code on stream that needs some algorithms and Mesh Optimizer that aren't there. And the third half is hearing people's feedback that they are enjoying the streams and that they are useful, which is awesome. So yeah, so it's been 2 hours, but I want to do draw indirect. Not complicated like draw indirect, you know, craziness with culling and stuff like that, that we will be doing next week. But I want to just say, hey, at this point, our draw loop is weird. It's saying for every draw call, push constants, and then, you know, submit draw call. There is a better way to do this that we can use. So in, like, if you only wanted to draw kittens, which, you know, kittens are awesome, then you don't need to do draw indirect, because you can just, like in here, we could have used instance rendering, and instead of push constants, we would upload everything to a storage buffer, and then we just would index the storage buffer based on the instance ID, which is very valid, a very reasonable way to do this. Similarly here, instead of doing this, and I think we did this before at some point, we could say, hey, let's submit more tasks. So let's submit the like number of tasks times like mesh, like draw size or something like this, right? And then in the shader, whenever we query a meshlet data, let's just take the index of the task, and we did this like yesterday at the end of the stream, I think. Let's just mod it by the like number of somethings, like number of meshlets, and here you go. Like manual instancing is doable with this approach as well. However, our real goal is to not draw however many kittens we are drawing right now, 3,000 kittens. It's to draw varied meshes, right? Like, I don't unfortunately have a second kitten model, but if I had a second kitten model, it would be so awesome to have different kittens around, you know, in this amazing world, instead of just one. So, and once we start doing this, instancing becomes problematic, because instancing can only instance the same kind of mesh, and I don't want the same kind of mesh, I want different meshes. To fix that problem, we will want to use draw indirect. So I want to get my feet dirty with draw indirect, just to sort of see whether it works, which I think it should, but who knows. And then we can do, not today probably, we can do more than one mesh. And then we can start, so I think basically next weekend we'll do something like, let's draw more than one mesh kind, right? Like let's, instead of just kittens, let's draw kittens and something else. And then let's start culling these buffers with draw indirect data, and like maybe start thinking about occlusion culling and things like that. I don't know. But for now, I just want to say, hey, like, so in debug mode right now, right, we are having to submit like 3,000 draw calls, and we are spending 22 milliseconds of CPU time, and I think it's basically all just debug validation layers, right? Which is not terrible, but we don't really need to do that if we can just use draw indirect. So What I want to do is just that. Let's do that. Again, I have not done this before, so maybe we will fail. But it should be, I roughly understand the idea. Oh, hey, BetCC. Hope Jailbreak is doing well. So, alright, so let's do this. So the way this works, and let's do this for the... I guess the pipelines are really the same. So the way this works is instead of submitting like mesh tasks in one draw call, there is a command called draw mesh tasks indirect NV, and there's also indirect count NV, but I think we only want this for now. For now, this is simpler. We will need to use the other thing when we start calling the meshlets, but for now this is good enough. And so the way this works is that you need a buffer. You need to pass it a buffer, and you need to pass a draw count, but it infers information about every single draw call from this buffer, in this case using these guys, right? So you have to essentially pass it a buffer of structs where each struct is 8 bytes. There is task count, first task, and it will use that for rendering. Inside the task shader, you should get something called draw ID or draw index. Yeah, draw index. You should get GL draw index that tells you which draw call are you rendering right now, which will be helpful because that we can use to read the transform data, right? That right now we are using push constants for, but we can't still use push constants for that in that framing. So we basically will need two buffers. One buffer will have the like this mesh draw structure, wherever it is, mesh draw, and the other buffer will have the indirect count parameters. However, what I'm kind of wondering about, and then for the for the non like mesh shading path, there is VKCMD draw indexed indirect, yeah, which is the same thing really, but it has, where was this? Or we just, oh yeah, Vulkan Core H. There should be a struct for that as well. Oh, and I guess we need to yeah, we need to tag this buffer in a special way, so that we can do. That we don't need for now. Don't need that for now. Oh, we need to explicitly request, I think, the ability to use this feature, which makes sense. There's also max draw indirect count. Will this interfere with our aspirations? What's the limit of this value? What? Oh. So we are guaranteed that we can render at least 65,000 indirect commands. Which is not terrible. It's also not amazing, but maybe the actual NVIDIA limit is higher. We shall see. Yeah, and then for the draw index path, you need to submit this thing. So this thing is like, what, 5, so that's 20 bytes. And then the NVIDIA command was 8 bytes. 28 bytes. So what I kind of want to do, okay, and this might seem weird, but it'll simplify the management of all of this stuff. And this might be a bad idea. This might be a terrible idea to do in hardware. I don't know that. But nobody's there to stop us. So here's what, seems to be an interesting idea. What if these commands, so this command data, like the GPU has to be able to read this to do draw indirect. And we have the data for the non-RTX path, which we still need to support because we support switching between them, right? Which is what, like 532-bit integers. And then there's the data for the NVIDIA thing, which is 2 integers, which is much nicer, much shorter. But together, this is 7 integers, right? So I'm kind of wondering, should we just burn the space inside the mesh draw structure for the 7 integers worth of command data? Or we can make it 8 for good measure, so that it's all like aligned and stuff. We don't need it to be aligned, but And once we do that, we'll just have a giant buffer with these mesh draw structures, where each draw structure is self-sufficient. It says what mesh to draw, which is the common data, and where to draw it, which is the position scale orientation. And then we'll just draw indirect from the same buffer and bind the same buffer as a storage buffer and read the mesh data from it. And it'll be glorious and amazing. So how about that? I think that will work. So let's try this. Yeah, let's just say that it's 7, and let's just make a union here on the C++ side, so that so there is a command data 7, and then there is the struct, which contains this guy first. Like, if we don't need the backends to work concurrently, like if you don't need these two rendering approaches to work concurrently, we don't need both, but I want them to still work concurrently. So this will be like command indirect, and there will be the other thing, which is indirect nv something, this guy, right? So that will be the command indirect, let's just call it NV or MS for mesh shading. And so this is 5 uint32s, and this is 2. Right? And then on the shader, we'll just say, hey, there's some opaque blob of data here. And just like ignore it, just like something happens in it, doesn't matter. And this is not wrong. This is not the correct type. Yeah. Right. So now let's migrate this data from a push descriptor. Let's migrate it to a storage buffer, and use the indirect command, right, to draw this stuff. So and the only thing is we need to do the same like upload thing again, but it doesn't seem too problematic. Feels nicer to move these guys here. Yeah, so we are saying, hey, let's fill the draw data, and then let's fill the command data for each draw. So let's start with the usual indirect stuff. So this is what it needs. Come on, where are we? Wait. GI doesn't work. Okay. So, like, let's just mem set the entire command data pretty much with 0. Because I'm not sure if it's done for us. It is done for us, but it's fragile to rely on that. And then let's just fill the things that we need. And this is the same arguments that we are already passing to the draw command. So we have the index count, which is basically mesh indices, right? We have the instance count, which is 1. First index 0, vertex offset 0, we aren't even using that. We aren't even using the pipeline associated with the thing that might want a vertex offset. So it's unfortunate that we are burning space on this, but what can you do? And then this is all 0, right? And then we will use the task, we will set the task thing to, it was like mesh let's size over 32. So that's the exact same commands that, the exact same data that we are already passing in each draw call. Right? Now let's upload this to a buffer. So we will create a buffer and we are running out of short buffer names. What is MB even? This is meshlet buffer. All right, but I guess this will be DB for draw buffer. Yeah. And we could maintain both paths. And in fact, for now, we can maintain both paths. It seems easy to do that. So let's see. A large buffer, we will use it for two purposes. One purpose will be draw indirect, so indirect buffer, and the other purpose will be buffer usage storage buffer. On some GPUs in some cases, and I have not worked with indirect draw calls, I don't know if this is the case. On some GPUs in some cases you can pay like a penalty for specifying too many flags like this. Like maybe on some GPUs if you use indirect and storage buffer in the same sort of buffer, you have some sort of penalty. I don't know if that's true. We will assume that it's gonna be fine, and if it's not gonna be fine, we can rework the data structures later. And then we'll do upload buffer. And then Vulkan doesn't have to support draw indirect, but we will just assume that it does, like that our adapter supports draw indirect. I don't know if Intel does, and I can't check right now because of bugs that I have talked about on stream before. But we can do this later. Like offline, I'll check if this code works on Intel GPUs. So yeah, just upload the size of mesh draw, and then draw size. Wait, draw. Hold on. What's wrong here? Q buffer. Oh, scratch. We need to specify the scratch buffer, right? And let's do in the same fashion. Let's do like draw indirect enabled, and then we will toggle that. We'll start with false, or we'll start with true actually, but let's say whenever I press I, we will reset it. I guess I can, are we like initializing this too? Yeah, I can do this. This makes more sense. Oh, but if I wanted to maintain both paths with projection stuff, it will be really painful. For now, we will hard code the projection matrix. We are doing this like late matrix update here. For now, we will stop doing that and just like upload this thing once. And if draw indirect path actually works, might have to remove the other path. Yeah. To do basically, well, actually it's probably fine. I think it should be fine. So if we are not using the draw indirect, then we will update this stuff, and let's just fork the entire thing for now. So we'll have like 4 options now: mesh shading and draw indirect, 4 combinations. We will stop doing this, once we confirm that like the reason why I want to keep 2 code paths is I want to compare performance. Like for every single thing that we've been doing, we've been carefully observing performance before and after. So I want to keep both paths for this for now. So okay, like if draw indirect is not enabled, then we do the same thing that we've been doing before. No changes. If it's enabled, so we still need to pass a projection matrix that can change every frame, and let's still pass it via push constants the same way as we've been doing before. So let's just create like some sort of dummy draw, and then pass a projection matrix, and we'll clean this stuff up momentarily if things work. I just don't want to like commit code with draw indirect as the only option if somehow it's twice as slow, and then like what are we gonna do, right? So I want to keep both for now. So then with mesh shading, what we're gonna do is we're gonna push our descriptor stuff, except that we need a new buffer now. Oh, but we need to fork the shaders. How am I gonna do this runtime switch if I need to fork the shaders? Alright, let's hope for the best. Let's just hope that draw indirect is awesome. And, you know, we won't need to, like, yeah, let's just hope that it's awesome. So then we might as well split the projection matrix into, I don't know, let's call it globals for now. Yeah, I forgot that the shaders have to change, and I don't wanna, that's like just too much work to maintain both paths, because we don't have like defines in the shaders and stuff. So yeah, let's hope it works. Let's hope it basically is fast, right? And then if it's, because we know the numbers, we know like it was like 23 billion triangles and like 15 billion triangles or something for the like fixed function path. So let's just hope that it's good. And then if it's not good, we can, I don't know what we're gonna do. We need draw indirect. I don't know if what we're gonna do if it's slow, but I'm hoping it's fast. So we are still gonna use push constants to set the projection matrix that I just moved to different struct. So still need that, but instead of draw it now will be size of globals. Oh, and when we do when we create the pipelines, we need to say that this is our, yeah. And then we need to bind the buffer with the draw call data. And it would kind of make sense to reorder these things. They're like ordered in a sort of weird fashion right now. Like what would make most sense to me is that the first thing is the draw buffer, and then we have meshlet and meshlet data buffer, and then we have the vertex buffer, because this is kind of how the ordering works for different stages. Like the task shader only needs to read draw buffer and meshlet buffer for culling. The mesh shader needs to read also the meshlet data buffer and the vertex buffer for vertex data. So this seems like a nicer order. So then we'll push the globals via push constants, and then we'll just draw everything with one draw call, and then hope it works. I dearly hope it works. So what was it? Wiki CMD draw mesh task indirect NV. Not using indirect count version yet. That might happen next stream or some stream after this, or who knows when. So we need to tell it that we'll be reading data from the draw call buffer. Should work, I don't know. From a 0 offset, all the draw calls. Oh, the offset is peculiar, hold on, yeah. So the size of each struct is how many bytes the GPU needs to skip. Now for the NVIDIA thing, we need to start reading data from where our command data for NVIDIA is inside the mesh draw structure. So this is command indirect ms, I think. And then for the non-NVIDIA thing, we need to be doing something very similar, but the offset is different. So instead of this stuff, here we also will need to pass the draw call buffer, I think. Yeah, because this is where we need to read the data from. We still need the index buffer for this path, so that is correct. So I think that is all good. Oh, and also that way, right, the draw call buffer can be number 0 in both variants, so we can still, in fragment shader, if we need to read something from the draw data, we still can. So that's good. Right, so that should not read. Okay. So now instead of the mesh tasks indirect in the non-mesh shading path, we need to call cmd draw indexed indirect command buffer db buffer, and then offset button of a different command, and then same thing. Alright, and remember, there's no debugger. If any of this code does not work, we are screwed, right? If this code works, then we are golden. So, on the GPU side, we need to do the same global split. And now the mesh draw will be in a buffer with all of this redundant command data that is, like it can be faster to split these guys into 2 structs, of course, because then the GPU will not, the GPU reads will be coherent, but it should only start matter for relatively large draws, and it's so nice to keep all of this in one struct that for now we'll go with that, assuming it works. So now we have to go through all shaders and sort of make sure that things are correct. So in our first shader, in the task shader, we have globals struct that for now only has a projection matrix in the push constants, and we don't even need this because we are not using the projection matrix for the task shader, so we can just remove this. And then we have buffer 0, which is draws, let's call it that. Mesh draw. In fact, we could have called the structure draw instead of mesh draw, but that's fine. And then buffer 1 is still meshlets, so that's good. Now inside here we should have our draw call index available via GL draw index, I believe, which means that I think this should work. So let's just read this from. We were careful to not do this kind of structure readout for the purpose of keeping the 8-bit integer stuff working because of really unfortunate limitations right now with that kind of stuff in GLSL and SPRE. But this for now just doesn't use any of the 8-bit stuff. So for now, this just simplifies our code drastically, and we'll see if we can keep it later. And I think that's it. I think that's the only thing here. We will want to do some more work with the shaders once we start drawing more than one kind of mesh, because right now we still have one kind of a mesh, right? But this can happen later. And yeah, so that's it here, I think. Now we need to go to the mesh shader. So this changes substantially, right? So there's a draw call, then we have reordered the buffer bindings so that the vertex buffer is last essentially. And then our uniform structure only stores the globals, which is only the projection matrix. So let's look at that. Draws, meshlets, 0, 1, 2, 3, seems fine. And then do the same thing where we do mesh draw is draws GL draw index. The rest should be fine, really. And then finally the vertex shader that is not using the mesh shading path, right? So same thing here. And then we have to reorder, so this is buffer 1. This is draw call buffer, and the globals contains globals. Oh, and our shaders should stop compiling because GL draw index undeclared identifier. Now we'll have to hunt down which extension we need to enable for this, which is always fun. Is it like maybe just like this thing or something? So for this you need GLR shader draw parameters. Let's see if we can just look at GLSlang source code for draw index, if it even is supported. Oh, it converts draw ID to GL draw index. Oh, and there are some tests. Tests are nice. I like unit tests because it should be easy, hopefully, for us to like look at the shader code that's valid. SPV draw, if we can find it. Draw params. These are shader out. Oh, I see. This again. Yeah, so basically, I guess we are supposed to use GL draw ID arb in the shader code, but it translates to draw index in this PRV. That is confusing. But at this point, we have seen many things that are confusing, so we don't care. So yes, let's use GL draw ID arb. And in the mesh shader, we need the same extension and the same like thing. And in the task shader, we need the same, wherever the extension was, and the same thing. Oh, okay. So this compiles. This shouldn't compile. Yeah, because there is no projection. Now we need to read projection data from the globals. And same in the mesh shader. And maybe we are done. I didn't enable a couple of things. I didn't enable like anything really on the C++ side. So I'm expecting validation errors. But they should be easy to fix. There's warnings. There's always warnings. Okay. What? Wait, no, this never happens. Okay, at least one of the paths is broken. Oh yes, this is because we didn't enable the feature, but this just worked. Wow. Okay, this is really unusual. These things do not happen. Okay, yeah, so the validation layers are telling us, as I have expected, that we need to explicitly request the draw indirect, no, not this one, the multi-draw indirect feature. Because we are using draw indirect, basically, with more than one draw call, right? So if it's not available, we are, you know, like it will not be good. So both paths work. It's amazing. Every time we do this, we forget to destroy things. But this is why validation layers are there to help us. We called it DBA, but I think we created it after everything, so the logic, okay. Okay. So now how in debug, now we are running at 60 FPS instead of like 50 FPS or whatever we were running on. Because now, like, validation layers cannot really check the contents of each draw structure. So if a draw structure is broken, you know, there will be a bug that we cannot find easily. But on the flip side, why is process memory larger? It's kind of interesting. I thought these buffers would not map into. Oh, we are mapping. No, we're not. It's kind of odd. Anyway, on the flip side, we are rendering everything with one draw call, which is nice. And let's check that with vsync, I'm not expecting things to be slower because there's no way we are bound by, you know, there's no way things are going to be slower, but let's check. Yeah, so we're still reaching 23 billion triangles per second, so that's cool. How many, you know what we should do? We should measure the number of meshes per second that we are doing, otherwise known as kittens per second. So let's just do that. So this is just the same thing that we were doing, but except for that. And this millions. I think it's like not millions, but it's like hundreds of thousands. So let's do aspirationally, let's do millions. And then when we start culling things, we will actually start probably doing millions. Yeah, so we are rendering like 800,000 kittens per second still, which is consistent. Like draw indirect didn't save us time, but we are not rendering that many meshes, right? Like it's only what, like 1,000 or something, or 3,000 I think. If each mesh was simpler, then we would potentially be saving very valuable time. For example, let me commit this code first, because this worked. This was amazing. Oh, vsync. I can't really compare. This is the problem, right? So like I can't really show you that draw indirect would save us time, because for me to show that we'd have to flip back and forth between different versions, and it's kind of painful to do that. But this worked. This was amazing. Yeah, like this just worked with interleaving command data, which I didn't know that it would work within the storage buffer, which is nice, because for now it helps us sort of manage the code. We may decide it was a bad idea for performance one day, but for now this seems fine. D10 draw indirect. We've converted both traditional rasterization pipeline and mesh shading pipeline to draw indirect, which will be helpful. It's not really helpful now, like we're still running at the same speed, right? But it will be helpful later for GPU side mesh culling and etc. I mean, it's really mostly GPU side mesh culling that I'm interested in. But this moves all of the data that we have to the GPU, right? Like we still have the draw, like we still have a bunch of state vectors that we just aren't cleaning up on CPU. But basically all of the data at this point is on the GPU, which is nice. So, all right, yeah. That's the final thing that I wanted to do. We are running a bit, later than usual, but this seems fine. Come on, stop posting stuff about Roblox. Don't post Roblox questions. I will not answer Roblox questions. Black program on the mouse. I don't know what you're talking about, sorry. Alright, so yeah, this was it. We have successfully used draw indirect, and we have like a 3 pipeline with depth buffer and projection matrix and everything, perspective projection matrix, and everything works and everything is still fast. And we're using GLM, so if we need to do more math stuff on the CPU, it will make it easier for us. Even though our GLM use is really super limited, right? We are basically using GLM. I don't even know what we are using GLM for. We're using like GLM structures, and we're using like a function from GLM. So, but one day maybe we'll use more of GLM. So maybe that'll be a good investment. Yeah, so if anybody has questions about anything that we have done today, then I will be happy to answer them, but I will keep it short because I will definitely want to end in like 5 minutes. This stream is slightly longer than the usual stream. So I don't want to delay it too much. But this works. This is great. We can double check if anybody has questions while they're writing them in chat. Let's render some other mesh. So this is my old Roblox character, which is really big. But now we have superpowers. We can like scale things and stuff. So let's scale this mesh down. This mesh should have fewer triangles, substantially fewer triangles, I should say. So yeah, let's like divide by 10 or something, I don't know. Okay. And now let's just go nuts and have 30,000 of these guys. All right. Cool. So we are not as well, we are not VSynced. I mean, we are VSynced, but we are probably not as efficient as we were with kittens. Yeah, so we are running at, like, let's call it 13 billion triangles per second, right? This is sort of expected, so this mesh is not as, like, it has few triangles, right? There's a lot of these guys. Now we may be actually hitting some kind of mesh draw indirect limitation, or maybe not. But it's expected that we cannot saturate the rasterizer in all cases. Oh, and the other thing that we are doing, we are still rounding the meshlets to 32, which we don't need to be doing, but that generates some extra work that's redundant. And in this setting, we are running at roughly the same speed. Actually, we're running like slightly slower with the mesh shading on, which is like if we stopped rounding the meshlet stuff up, then this would make sense. But this is a pretty low poly mesh, relatively speaking, so that's not entirely unexpected. We can use some, I don't really know. Oh. I don't know what. Oh, this mesh doesn't have normal data. So in this case, we are running faster with RTX. Oh, I think this mesh has roughly the same number of triangles, but the triangles are like structured in a way that is more efficient for the RTX pipeline. But anyway, with like this stuff, right, so we are basically at 60 FPS. We are, without really breaking a sweat, we are rendering like 30,000 draw calls, and they're still relatively heavy. They're a few thousand each. With a smaller is Arctic Fox. So this is like 1.7, 1.8 K triangles, and this is like a really inefficient mesh, I think, in terms of the vertex utilization, because it has lots of faceting going on, right? But we are now rendering 30,000 at like basically, what is it, like 120 FPS, right? And it's not kittens per second anymore, but let's just keep this metric, this is fun. Same thing, actually. It looks like when you have a lot of low poly stuff, the traditional pipeline currently is faster, which is unfortunate. We will need to look into how we can make things better, right? It could be that indirect dispatch is not as heavily optimized, and we cannot use indirect dispatch in quite the same way, but it's gonna be a bit painful with more than one kind of mesh. So I'll think about this. Maybe there's something that we can do here to, when there's like a lot of low poly meshes, make the RTX path faster. For high poly meshes, we need to start doing level of detail, so that'll be nice. All right, anyway. All right, nobody is asking any more questions, so that is good. And now we can, I will like revert the modifications that we have just done, so that we are back to kittens for now. And it sounds like we have some work to do on figuring out if we can get the RTX path to be faster for low poly content, which right now it's right now RTX path is faster for high poly content, but slower for low poly content. It's not like substantially slower for low poly content, but for really low poly content, it's really visible. So we will need to see if we can make it better somehow, but that'll happen next week. All right, thank you everybody, and let me end the stream.